Hi, my name is Paddy Delaney from Huber, and today I would like to discuss our white paper on sizing of temperature control units for reactor applications. From my background in process and medicinal chemistry, I moved to the temperature control world after doing a bit of reactor design. And what it hit home to me was a lot of people, whilst they understand the calorimetry of their chemistry, applying this to scaling up chemistry doesn't always give the same results because of a misunderstanding on the sizing of the TCU units for the applications. So if we think about it, if we look at the energy balance of a reactor system, classic calorimetry tells us if we put in reagents A and B, you either apply heat or you take out heat and you get out product C. This temperature profile can have a dramatic effect on product ratio to isomers, product purity, polymorphs. There's many applications in the chemistry world where correct application of temperature is crucial. Whilst most people will, during their scale-up process, look at the calorimetry, and what I mean by that is, do they have to apply heat to get a reaction to work? So, for example, an endothermic reaction. So here we've got a picture of a toluene reflux, where we're heating up the reaction system to 80 degrees C to promote a chemistry reaction, and that can be seen by the yellow color on the reactor system. Or is it an exothermic reaction, where we need to control the temperature of the reaction based on the heat output of the chemical transformation? So here we've got a thermal image of a lithiation done on process scale at -40, where we want to hold the process at -40. But to do this, often the jacket of the system will be below -40, and you'd need that delta T to keep your process at a steady temperature. Why did I make the statement earlier that whilst a lot of people understand their calorimetry, they often don't scale up properly? Think about your reactor systems. Here we've got two different reactor systems. We've got an 80-litre reactor and we've got a 50-litre reactor. What we can see here from the thermal imaging is heat loss to the environment is minimal in this 80-litre glass-lined stainless steel reactor, which is highly insulated. Whereas if we go to a glass reactor system, we see at -40, we see a great heat loss in the environment. So that's the deep purple cover. So we're losing it outwards rather than getting that thermal energy inwards to the chemical process where it's required. So step back a bit and think about the reactor systems. Yes, it's key to understand your reaction calorimetry, but what we also have to appreciate is the process is carried out in a reactor system. And here it can be glass or stainless steel or glass-lined stainless steel. You also have an impeller inside of your reaction medium stirring it around. You may have baffles, samplers, PT100 probes, all made of different materials, such as PTFE, glass or steel, or Hastelloy. We have the reactor volume. Do you perform your chemistry at full capacity, like a crystallization? Or do you work with resins where they swell so you only fill it halfway, knowing that at the end of the process, it'll be full? Key to getting the thermal energy across is knowing your reactor jacket capacity, because this is the interface of efficient thermal transfer. And then following off that, your HTF feed and return lines. Are you using a TCU just outside your fume cupboard, or is it in a plant room? We have to take this into account on top of your calorimetry to work out how much heating and cooling is required in your reactor system. So at Huber, we've been working hand in hand with chemists since the early 80s to develop, well, initially it was our open bath systems, which moved on to our high performance Ministat systems. And the Tango has been on the market since 1988, when the first Ministat hit the lab, basically. So, key is to know which unit do we pick, how much cooling or heating power is needed. To do this, we have to look at the information I just discussed about our system profiles. And yes, we can apply a bit of maths here, which is always beneficial. So what information do we need when calculating the TCU. So if we look at a quick calculation, so we've got Q is our power. Now bear in mind, if you get a negative value, that's cooling, a positive value, that's heating. So we need to know the weight times the specific heat capacity of the materials in your, I'll call it system, plus the weight times the heat capacity of your thermal fluids, plus the weight times the heat capacity of, we'll call it reaction media. I'll appreciate you might have many components in your reaction media, but the key player here is your bulk solvent, because that's the largest heat sink you have in your system. You might only have a 2, 3, maybe 10 mole % of other chemicals in there compared to your bulk system. So we then multiply that by our delta T. So that's the difference between your starting and your end temperature. Obviously positive if you're heating, negative if you're cooling. And then you divide that by your ramp time. This is our basic equation for calculating heat capacity, or heat loads that are needed. So I've put these 3 sections here. What does that actually mean? If we take a reactor system, all right, this will be a very crude drawing, but it should get the point across. Say this is our glass reactor. We have an impeller in place, maybe a PT100 or a PAT probe. We have our jacket. We have our inlet and our outlet. So as normal, we've got our inlet at the bottom, our outlet at the top, and of course we'll be using a Hoover on this system. So if we look at system, what I mean here is the overall weight of materials. So in this system here, we would say, if we're using a glass reactor, a stainless steel impeller. So we need to look at a worked example here to fill this out a wee bit better, so it makes a bit more sense. So if we were to take example A, we have a 50-litre reactor. We're using toluene, 50 litres, and the temperature range is cooling from 120 degrees C to minus 30 degrees C over a 2.5 hour period. So our ramp down is 2.5 hours. So if we look back at our prime equation here, we have our time, 2.5 hours. We do need to convert that to seconds. We have our delta T, so it's minus 150. We're going from 120 to minus 30. We then look at our reaction medium. We know it's 50 litres of toluene. What we need to work out is our system and our thermal fluids. So this is where getting your P&ID and your specification drawings from your reactor manufacturer is important. So if we call this A, this one B, and this one C. So A is our system. So we'll call this A. And this is the weight of reactor plus auxiliaries. B is our thermal fluid. So B, if we just draw a funny bracket around it here, so B is HTF in jacket plus fluid lines. And then C would be this fluid in here. So that's our reaction media. So let's start doing our calculations then. So the material we have are glass and stainless steel, 316 in our system. From our P&ID drawings, we know we've got 60 kilograms of glass. We're at 10 kg of steel. Our HTF, so we'll label that A, HTF. It's a Huber-Sill oil, so all the specific heat capacities and stuff like that are found in our thermal fluid brochure, but we know we've got 25 litres. And C, we've got our reaction media, in this case toluene, and we know we've got 50 litres. So we just need to do a bit of conversions on this to get the values right. So we know our density is about 1.01. So let's just say our HTF is 25 kilograms and toluene is not far off 1. So let's say we've got 50 kilograms of toluene. We then need to multiply by our specific heat capacities. Again, you've got Wikipedia, the Aldrich catalogue, Huber catalogues for our heat capacities, but they're all quite well known. In the case of glass, it's 0.91 kilojoule per kilogram Kelvin. Stainless steel is 0.51. Our Huber-Sill oil is 1.655 and our toluene is 1.612. So we have that. So then we can work out our mass times our specific heat capacity. So obviously we're going to multiply this value by this value, so our kilograms will be removed and you'll be left with a kilojoule per Kelvin. So in the top case we were at 54.6 kilojoule per Kelvin. Our stainless steel is 5. Our HTF is 41.4. And our toluene rounds it off at 80.6. So we'll just use the same units there. So we now have all of our base data that we need. The last thing to convert is just make note of our delta T is 150 degrees. Doesn't matter if that's Celsius, Fahrenheit, Kelvin, it's a degree. And we've not put an exact unit. And our time in seconds would be 9,000 seconds. So T equals 9,000 seconds. So if we then put this into our power calculation, we have Q is equal to, let's do some big old brackets here, 54.6 kilojoules per Kelvin plus 5 plus 41.4. I know I'm going through this quite in depth and explaining. This is the key equation essentially when looking at this information. So we're going to multiply that by our delta T minus 150 degrees, and then all of that is divided by 9,000 seconds. So where that gets us to is Q equals 181.6 kilojoules. We can lose out the kelvins in a second, which will make life a bit easier, times minus 150. We can assign Kelvin because on that, divided by 9,000 seconds. We are then left with Q is equal to minus 27240 kilojoules per 9,000 seconds, which gives us Q is equal to minus 3000, 3.0226 kilojoules per second, and 1 kilojoule per second equals 1 kilowatt. So we can see from this the power required to cool our system down is roughly equal to 3 kilowatts. The negative value suggests that we're cooling. So we need 3 kilowatts of cooling power to cool our system from 120 to minus 30 in 2.5 hours. If we decrease the time, obviously the cooling power will increase. If we decrease the time, it needs less cooling power. But essentially that is our worked example. And this can be applied to any systems if you break it down to the basics of cooling power is the heat capacity times the weight of the system times the thermal fluid plus the reactor medium, and then simply multiply that by your delta T and divide it by the time rate you're looking for. So I know that's quite a complicated system, but at Huber we like to prove our mettle. And what we've done is, if you compare that to case studies of a similar system, we could see that we have a 510W system here, cooling a ChemGlass 50-litre reactor from 120 to minus 30 in roughly 2 hours. So while it's important to do the imperial calculations, sometimes a real-world test is needed to double-check the values that are given. And at Huber, we don't hide our case studies, and we perform them to DIN standards or better. So look at the Huber website. It'll show you relevant case studies for the size of reactors. We're always quite happy to talk through your calculations for your system to give you roughly where you need to be, but case studies do prove the point. Now, we're often asked about condenser systems on reactors, because whilst people are performing chemistry, sometimes they're distilling off solvents or doing an azeotropic distillation to remove their product. When it comes to distillation, you've got to think of your environmental factors again. Whilst we're heating your batch of chemicals, they're going from liquid phase to gas phase, and then back to liquid phase again. But you're losing heat to the environment. And from when I finished my PhD in Sheffield back in 2007, I've performed many distillations. And one thing that's always static is the heat source. They're often electrical or they're set kilowatts. So we know we're applying X kilowatts of heat. What you'll see then, to get into the gas phase, by the time you're in gas phase, you still have 2/3 of that heat energy left in your gas, because you'll feel it warming up the reactor side, or you'll see it condensing on the lid or moving up. So typically at Huber we go, in the gas phase you're at about 2/3 of your kilowatt power. To get up to your liquid phase on your condenser, you're normally at 1/3 of your initial heating power. So if we've got a Unistat with 3 kilowatts of heat being applied to the reactor system, typically to size a condenser, assuming you've got an efficient condenser system, is about 1/3 of the heating power being applied. So we've done the calculations to see how much heating or cooling power we do. Now at Huber, we're quite fortunate. We make some very good open bath systems, and we make some fantastic Unisat systems. But depending on the customer's budget, application, where they're housing the application, they might be able to use an open bath system or the more high performance closed systems. So how do we compare these? Well, first thing we do is we often look at case studies. The closed systems, also known as Unistats, are designed to deliver the most efficient thermal transfer with the smallest quantity of thermal fluid. As a result, you get high watts per litre value. Whereas an open bath system might have a lower watts per litre value, but they'll still do the job. So if we were to take, for example, a 1 litre reactor system, here we're using a Radley's 1 litre reactor system, and we hook it up to a heater bat like a CC308B. And we're heating from room temperature up to 195 degrees we see that our open batch system would do that in about 47 minutes on the process value, whereas the jacket temperature tends to get up there in 24 minutes, which is pretty good. Open batch systems, obviously the oil is open to air, so sometimes you might get cracking of oil or a wee bit of a whiff of smell in the lab because you're boiling out. If we're to compare that to our chili system, which is it's our smallest Unistat that we actually build, on the same 1 litre reactor with the same batch of oil, we can go from room temperature to 190 degrees 10 minutes faster. So on the process, we hit it in 35 minutes, and on the jacket, we hit it in 15 minutes. But in addition to that, the system doesn't get hot on the outside. There's no vapors or anything like that. Key is it uses a lot less energy to heat up. So whereas our open batch system might be applying 3 kilowatts of heat all the way along, our chili is only applying 1.5 kilowatts because it's a more efficient system. So whilst you might pay a little bit more, you're using less thermal fluid, using less electricity, and you're transferring your thermal energy a lot more efficiently. So you can get a higher rate of process, and you can perform more batches basically. So that's on the heat up. If we look at Subzero systems, again, we're going to use a Radley's reactor system here. And in this case, we're going to compare a Huber Ministat 240 versus a Huber Petite Fleur on the same reactor, same oil, same conditions. And this is, again, shows the difference between open bat and closed bat. The open bats have a larger volume of fluid, so they have a smaller watts per litre ratio. But you know, if we look at it, it's still cooling down pretty quickly, as we saw in the heat up cases. When we look at the Petite Fleur, we're able to cool down a lot faster and more efficiently. So this is why we have to look at location, budgets, stuff like that, because it might be that whilst a Ministat will do the job for you comfortably, get you there, you might find that you can perform more batches, or you're reducing processing time by using a Unistat. In addition to do I use open or closed systems, one of the key factors on performance of systems, where a lot of people get it wrong, is which thermal fluid do I use. Luckily, we have a very comprehensive brochure with the Huber Thermal Fluids brochure, which goes through all the technical data for each fluid. But there's some key factors you've got to remember with thermal fluids. Number one, when you're heating up, all thermal fluids have a specific expansion coefficient. Most of the Huber ones are about 12%, so for every 100 degrees, you increase by 12% the volume in your system, basically because it swells. It's not a problem because most of the Unistats have an expansion tank on them, which allows the fluid to move up into a temperature isolated zone, so it's never hot or cold. Or if it's an open bat system, it just expands into the bat. Not new, we've known about this for years. So it's always important to calculate your volume of expansion, and we can talk you through that if you need us to. Second to this is, how efficient is your thermal fluid? Here we can see a case study using a LabTex 1 litre reactor, just on our little baby K6 model. But we performed multiple experiments here. We performed a cool down using ethylene glycol water mix, a 50-50 mix. And we also compared it to using a sill oil in the system. And what we'll see here is the green and red are the process and the jacket temperature on the glycol water, whereas the blue and purple is the sill oil cool down rate. So whilst a customer has purchased a Huber unit, by using glycol water in it, you're actually not getting the most out of your investment. You can see here that the cool down to minus 18 from 100 took about 300 minutes. Whereas if we use a sill oil, which has about a specific heat capacity about half of glycol water, we're able to increase the performance of the unit because we're able to transfer that heat energy a lot more efficiently through the correct fluid. So cooling down from 100 to -18 takes about 150 minutes. Obviously, if you want to go quicker, you get a more powerful unit with more cooling power. But this is only our little baby K6 model. It's quite popular for benchtop reactors. But key is use the correct thermal fluid and you'll get a lot more performance out of it. The other side of thermal fluids to be careful of, so you get the correct one, is that they all have different viscosities at different temperatures. And in our brochure, we do give a viscosity versus temperature graph. And what you'll see in most of them is, say for example here, we've got an M40 oil, which means it operates at -40. It's quite happy at -40. We'll get a 50 centistoke viscosity, but below that temperature, your pump may struggle to move it because it's nearing its pour point and it'll turn to like a wallpaper consistency. So we do have a nice brochure that explains where and when to use each fluid, and it gives you a traffic light system and their maximum minimum temperature ranges. So that's another one to be aware of. When it comes to glass reactor applications, a lot of people, alarm bells ring because we know glass reactors are pressure rated on the jacket to about 1/2 bar. But what does that actually mean? So if you looked at Huber product specifications, you can often get a pump curve and you'll see flow rates per minute. At Huber, we like to operate with high flow, low pressure. This means you get rapid thermal transfer because the fluid is moving. Some manufacturers say go high pressure, low flow, so that you get fluid through the system. But we're quite unique and we go the opposite way to everybody. So if we look at this pump curve, we can see most of our units operate at high litres per minute. If you were to deadhead, and by what I mean deadhead, is you put a valve in line and you shut it and the fluid cannot move, we can see that if you're running at 1.5 bar, you've got virtually no flow rate. So when it comes to glass reactor systems, there's two options. You can either dial the pump down a wee bit and reduce your flow rate, but this sometimes could affect your efficiency of thermal transfer, or you can fit a bypass to the system. We are generating another white paper based on the pressure in systems. So here, for example, we have our Huber unit and our application. We would put a bypass in here to allow some fluid to just leak past and not hit the application. Or you can fully automate it and have a VPC bypass where you can go from 0 litres per minute all the way up to full flow. And the unit will do this based on the pressure that you dial into the control panel on the front. So here we can see the gated here. We see our major flow and our minor flow. So we've gone through the main considerations. So yes, you've got your system calorimetry, you've got your system global setup that you have to take into account when doing your power calculations. We've looked at thermal fluids, and we've looked at, do we use an open system or a closed system, depending on your kind of budget restraints and what you're looking to future proof. At Huber, we're a strong believer in proving what we say. And we've got strong working relationships with a lot of reactor manufacturers. And you will find on our website, which is very good to work hand in hand with your calculation, is multiple case studies from all the way from a jacketed round bottom flask up to a 250 litre reactor, where we've done the case studies and performed full testing, including T-mins and timed T-mins, so that it makes life a bit easier for you to select them. So on this table here, we have kind of filled in the gaps a wee bit with my colleague Ken McKenzie on case studies we've performed and what units would fit in between the case studies from our trend data that we know this Huber performs like this. So highlighted in black, you'll see real case study data. The faded out are proposed units, but we're also working on those case studies. But if you go to the website, you will find a full selection of our case studies available and the multiple units that we've performed these case studies with. So in conclusion, the key points to take home from this webinar are you're using your total system calculations. to work out how much cooling power do I need to cool my complete reactor system, not just my calorimetry data. We're looking at the correct choice in thermal fluid, and we're looking at the kind of real world examples of the case study database that Huber have generated. We're always happy to test further applications if you've got a niche one, and this can be done at any of the Huber sites globally. With that, I'd like to thank you for your attention today, and if you've got any further questions, don't be afraid of emailing myself or get in touch with me on LinkedIn, or any of the local Huber subsidiaries. We'll all gladly help.